Now, okay, folks. So I hope that you guys enjoyed your weekend. I hope everyone's having a good start to their week so far. Um, it is the 28th, um, and we are talking about solutions. Um, I know that many of you guys are the ones who took the exam last week, and so you're probably like, well, where are my results? And I will get you the results just as soon as everyone's taken the exam. I would expect to see the results maybe no later than the end of the day tomorrow, because not only am I going to wait for everyone to have taken the exam, but then I'm going to go back and look, make sure that all of the questions were keyed properly. That's why I haven't released your scores because I don't want anyone to be like, oh my gosh, I got a 12 and then be like, oh, actually, and I would not expect someone to get a 12 and then get like a perfect score. But I don't want anyone to look at it and be like, oh my gosh, this is a score that I got, and then, you know, have it revealed that, oh, actually, I had miskeyed a couple of questions. So just if anyone is curious, today is also a day in which we are not going to be taking any sort of attendance, just like last Thursday was a day we didn't take any sort of attendance. Okay, so we've got solutions. Now, a solution is something that I always like to think about as being a little bit intuitive in some respects. Um, because you know about solutions, like coffee is a solution, salt water is a solution, um, tap water is a solution. Could anyone add to the chat? Um, like if I said, is actually give me a number in the chat if you're familiar with deionized water or distilled water. And many times people will get distilled or deionized water for like an iron or let's see what other like a CPAP machine. They'll get them for basically like appliances that have to have pure water. So, you know, I'm sure that some of you guys have encountered distilled or deionized water at some point in your life, and distilled and deionized water are basically just pure water. They don't have any dissolved minerals in there. So there's no sodium chloride, not even like a trace amount. There's a very, very small amount, or sorry, um, like compare that to your tap water. Tap water is a solution. Tap water has dissolved minerals in it. In Central Texas, if you think about hard water versus soft water, that's a good example of, well, two different solutions. Um, well, they are both solutions and they both just have more of minerals than less. Okay, so here's our important terms when it comes to solutions. We've got a solute and a solvent. Now, to put it simply, the solvent is the substance in greater abundance. The solute is the substance. All right, let me rephrase that. Is the oh no, dissolve. Oh, computer, why'd you do that to me now? So I installed the driver to get my tablet to work properly, but now it's throwing a curveball at me and it's switching me to my eraser. I don't want to use my eraser. Control P. Okay, so you go here. That gives me my eraser again. I don't want my eraser. Okay, there we go. So your dissolved substance. Strange. Now, over here on the right-hand side is the resulting solution, the mixture of your dissolved substance and your solvent. So the mixture of your solute and your solvent. Now, to the naked eye, something like salt water, you could look at a glass of salt water, you could look at a glass of deionized or pure or distilled water, and you're not going to notice a difference. But give me a letter in the chat if you would taste the difference between salt water and distilled or deionized water. Yeah. I had an older brother, and so naturally, when he discovered that salt could dissolve in water, I was his first test subject to be like, hey, I brought you some water, younger brother. And I was like, wow, that's so thoughtful. And then I drank it and I was like, this is horrible. He's like, ha ha, gotcha. You never saw it coming. You're right, I didn't. I thought you were just going to be kind. But alas. Okay, so whenever we talk about solutions, one of the things that I always think about, aside from table salt, is I always think about whey protein. Give me a number in the chat if you're familiar with whey protein and mixing it. So I always think about whey protein specifically because that helps me understand these terms, soluble versus insoluble. Now, I had a tendency to get these two mixed up, but what was helpful for me was to think about, you get some whey protein because you're like, yeah, I'm gonna cut down on my fat and sugar intake. I'm gonna up my protein amount. And so you're like, this is great. I got a shaker bottle. This is my shaker bottle that I'm gonna draw because it's a red cap. And then it's a glass. And then of course you got your little metal ball in there. So I can get my whey and I'm gonna add it in here. And whenever I add it in here, then I'm gonna also get some water. Because I don't want to mix it up with like milk because that would be too delicious. And if you're trying to like increase your protein intake, it can't be delicious. So you're gonna get some water, you're gonna get some whey protein, you're gonna start shaking it up, and then after it's all said and done, you're gonna get that glass, and let's just for the sake of simplicity, let's say that we took the metal ball out, so the ball is out, and you look at your solution, you're like, okay, cool, that looks I guess that looks like cookies and cream. And then you look at the bottom and there's some like caked on whey protein. And you're like, huh, oh well. I said I was going to do this, so I was going to do this. Now, what this shows is that whey protein, some of it is soluble. It goes into solution perfectly. It mixes up, and maybe the solution is a different color, but then some of it gets stuck at the bottom of the glass. It's insoluble, so it's stuck there, in which case, whenever you do go to drink it, what's going to happen is that insoluble junk is going to remain a solid. So basically, whenever you think about soluble versus insoluble, I want you to think of something that is soluble dissolves, and then something that is insoluble, no, or let me change that to does not dissolve. Okay, so with respect to that, we've got how do chemists think about something dissolving? And the way that chemists think about something dissolving or not dissolving, if it's soluble or insoluble, we've got to bring back this terminology, polar and non-polar. Now, if we look at something like sodium chloride, NaCl, is that a polar substance, or is there another term to describe that? If it's a polar substance, say yes. If there is another better term to describe NaCl, put a N in the chat. So when we think about NaCl, sodium chloride, well, let me just jog your memory for a minute because sodium, it's a metal. Chloride is a nonmetal. When we have a metal and a nonmetal come together, we make an ionic compound. So, is it polar? Well, it's really better to classify something like sodium chloride as an ionic compound as opposed to a polar compound. You could kind of think about it as so polar that it's ionic. Okay, now an ionic compound will dissolve very well in water. The reason for that is because water is polar. Okay, now I'm going to look at ethanol. This is your molecule of ethanol. This is carbon, carbon, hydrogen, 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 oxygen, and hydrogen. Okay, this group right here, OH, that is, well, that is a polar group. And so that makes this molecule polar. So a polar substance like ethanol, or in the case of sucrose, which has a bunch of OH groups, which is makes it also a polar compound. Polar compounds dissolve very well in a polar solvent like water. So a polar, let me write this out, polar or ionic solute, and this is, just kind of planning ahead for our next exam in the final. Think about this as, okay, well, how would I, what am I going to put on my index card, my 3x5 card, which just a reminder, you'll get a 3x5 card for the final. You only get one though. So your polar or ionic solute will dissolve, or let me change that to polar or ionic solutes are soluble in polar solvents. Okay, now as sort of a follow-up to that, I'd like some responses in the chat. What do you think, or do you think that a non-polar solvent, sorry, a non-polar solute, do you think a non-polar solute is going to be soluble in a polar solvent? If so, say, yes, I do, or if not, N, no. So NP, nonpolar solute, into a polar solvent. Well, the answer to that is no. A nonpolar solute is not going to dissolve or is not going to be soluble in a polar solvent. Okay. Now, an example of a nonpolar solute would be something like propane. Propane, you use that for your grill if you don't do like wood or anything like that. Um, and that is not going to go into water very well. That is going to be insoluble in water. Now, at the end of the day, we have this, or chemists use this kind of guideline, like dissolves like. So polar or ionic dissolves or is dissolved by polar. Now, the same thing is also true. So a polar uh, solvent will dissolve a polar solute. So I always kind of think about this as PiP soluble. Polar or ionic in a polar solvent is soluble. If you kind of switch them and you say nonpolar is dissolved with, or nonpolar plus a polar solvent, that's not going to work. Okay, so this is like a very important and good guiding rule when it comes to solutions. Like dissolves like, but you got to think about, okay, what is my example? Well, it's a polar or ionic solute and a polar or ionic solvent. All right, next up is dilutions. I always like to think about this as an example, or I always like to visualize this and think about like Kool-Aid. Gatorade, whatever, your Powerade, your drink of choice. Um, if you went to the store and got like packets of Kool-Aid, I remember when I was a kid, I would get like, the packets of Kool-Aid, and the packets of Kool-Aid said one packed, packet per, let's say, 1 gallon of water. And I was like, oh, wow. Okay, cool. I know how to do that. And then I think about it a little bit and I was like, what if I did 4 packets of Kool-Aid per 1 gallon of water? And as it turns out, this is much tastier. And why is that? Well, that's because I have a sweet tooth and I'm going to love the very rich thing. Okay, so yeah, this is tastier. And I get a Kool-Aid that was like you couldn't see through it at all. But that was not the prescribed recommendation. And that would be described as being a more concentrated solution. So if you've ever used like orange juice from concentrate or something like that, you get the frozen canister of orange juice and you add water to it and you make it more dilute so that it's, I don't know if I would go as far as to say healthier or healthy, but I would say healthier. Maybe a slightly lower dose of sugar is what you're hit with there. Now, this is an example where we can just sort of play around, and I'm going to go ahead and grab this link, and I will share this with you guys and show this to you guys. Okay, I'm going to grab that. Turn that. And then let's see, where's my browser? Close. Okay, now switch my share. This is basically going to show, hey, I'm going to make some Kool-Aid. I'm going to use some drink mix. I'm going to shake that drink mix into my half liter, my 500 milliliters of solution of water. And I'm going to keep shaking that. Oh, yeah, it's getting darker and 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 darker. And I could continue doing that. At some point, it's going to be too dark. But then I'll look at my concentration. My concentration is a quantity, a measurement. My concentration is currently 4.81 moles per liter. Okay, so that's a ratio. That ratio says I have this many moles of my drink mix in 1 liter of solution. But you can look at this right here and say, well, that's not 1 liter of solution. What this is saying is if you had 1 liter of solution, that would mean there's 4.81 moles in that 1 liter. But we only have half a liter. So the way that you would do this sort of calculation, I'm going to show in just a moment. But before I do that, I want you to kind of visualize, okay, well, how does the concentration change if we add more water? So I'm going to open up this spigot right here to add more water. Oh, as I add more water, what happens to my solution? It becomes much more dilute. And you see that with the color is lighter. It's gone from a bright or a dark, robust scarlet red to, well, a softer, almost like we're bordering to like a pinkish color. I'll add more drink mix and, oh, my concentration goes up. Now, if I wanted to see my concentration go up without adding any more drink mix, what could I do? Well, I could have some of the solution evaporate. And I see as I add more and more, well, what happens? My concentration goes up. Now, in this case, this isn't super critical to this class, but if you look, okay, my concentration as it is right now is 5.96. If I add more drink mix, my concentration doesn't change. Well, what's happening? Well, all of that drink mix that can go into solution has gone into solution. This is what is called saturated. It's almost like if you, let's say that you got a beach towel or something like that, and you threw it into the pool. That beach towel is going to absorb as much water as possible. And let's say that you got out of the pool yourself and you're like, oh, I'm going to dry off. And you pick up that beach towel that has been in the pool and you try to dry yourself off. Are you going to dry off because of the towel at all? No, you're not. The only thing that's going to happen is you're basically going to be pushing some water around. Lots of water is going to drip off of you, drip off of the towel. But that towel is saturated. This solution is saturated. The only way that you could get more and more of that drink mix to go into solution is if you add more water, in which case your concentration is going to go down. But at some point, you've added too much, in which case, well, your concentration like basically peaks. And this is from my own personal experience. This is when your Kool-Aid gets really tasty. It's where you've added like 12 packets and nothing else can be added. Okay, now we quantify, and that means we just come up with a number for concentration with the way that chemists think about numbers. Chemists talk about numbers and amounts in terms of moles. So, what we want to do for concentration is think about a unit known as molarity, which is moles of solute. Okay, so that's the thing that dissolves compared to the liters of solution. So this would be like saying the total volume. Now, I need at least one person. I need a response. This is super important. Um, let's say that you went to the store and you got a coffee mug, a coffee mug. And that coffee mug was like a science inspired one. And it had markings. It said, you know, let's say 500 milliliters. And what you did was you got your black coffee and you poured it into this coffee mug. And you poured it to precisely 500 milliliters. Could somebody tell me in the chat what volume of coffee you have? Perfect. We've got 500 milliliters of coffee added in there. Now, you know that it's 500 milliliters because you can look at it and you can say, okay, well, this demarcation or this line right here says exactly 500 milliliters. Now, let's say that you're the person who's like, well, I don't like just straight up coffee. I need sugar. And so let's say you get some sugar cubes. Let's say that you get like 4 sugar cubes and you add those 4 sugar cubes to this. Um, First of all, add a Y or an N. Will the sugar cubes dissolve in the coffee from your experience with, yeah, yeah, it will. The sugar cubes will dissolve in that coffee. Perfect. Okay. Now, my next question that's super important is is the volume, and I'd like a letter response, the volume of, or actually, okay, my next question is, would you agree that we now have a solution? We have the coffee plus sugar solution. Y or N to the chat. Perfect. The volume of our solution at this point in time, is it A, exactly 500 milliliters? And it was whenever you added the coffee. Is it B or C or D? D is unknown. Um, Actually, no, I'm going to change that to none are correct. B is less than 500 milliliters, and C is more than. So we've got our coffee. We filled it to exactly 500 milliliters. We added sugar. The sugar dissolved. Do we have A, exactly 500 milliliters, B, less than 500 milliliters, C, more than 500 milliliters, or D, none of these answers are correct? Perfect. We have C, more than 500 milliliters. Okay. Now, you're absolutely right. And thank you so much for participating in that. Would you agree with me that, well, the sugar, despite it being a solid, it occupies space. It has volume. Yeah, I think so. You guys took that into account when you came up with the answer of C. So this is an important thing whenever you're making a solution as a chemist, because you have to think about the solution, not necessarily, well, how much did I add? Because if you added 500 milliliters of coffee and then the sugar, let's say that the sugar ended up taking 10 milliliters, well, if you were trying to calculate the molarity of the sugar in the coffee, you wouldn't look at this and say, oh, okay, perfect. 5 liters of solution, that's 0.51, or sorry, that's 0.500 liters. Instead, you'd have to say, okay, well, the sugar is a part of that. So that's our actual volume of our solution is 0.510 liters. Can you give me a Y or an N if that makes sense? Perfect. Okay. Now, we're going to do calculations related to this and think about, and I'm going to show you guys how to make a solution. Now, this is another just sort of a simple display of how things work in terms of making a solution. What I'm going to do is well, we'll do these kind of as a group. What is the molarity of a solution made by dissolving 2 moles of NaCl in enough water? That language right there is some that I want you to kind of be attentive to. This doesn't say by dissolving 2 milliliters of NaCl in 500 milliliters. Instead, it says in enough water to produce 0.5 liters. Well, how much is this? I mean, it might be 475 milliliters of water. It doesn't really matter how much water it is because we're talking about a solution with a total volume of zero point 0.5 liters. So in order to do this sort of calculation, what we do is we look back at this equation. Molarity, which is represented by a capital M, is equal to moles of solute divided by liters of solution. We have our 2 moles of NaCl. So 2 divided by, and I'm going to say 2 moles NaCl divided by 0.5 liters of solution. Okay. Now this volume is the same as 500 milliliters. When you're doing a molarity calculation, you need your volume, which is in the denominator here. You need that to be measured in liters. Now, you don't need to do any sort of, oh, well, I'll multiply this by 2 to make it 1 liter. Don't do that. Instead, you can just say 0.5 liters. So effectively, we've got 2 divided by 0.5, which ends up being D4. Now, in the event that you see this sort of problem, I know that I struggled with this sort of calculation because it's like, oh, that's so simple. What I do is I say, okay, 0.5 is equal to 1/2. Okay. What I'm going to do is I'm going to plug in 1/2 in the denominator because I know that 2 divided by 1/2, what I need to do effectively is multiply what's in the numerator by what's in the denominator of my denominator. Now, if that made it more complicated than you feel like it was worth, then just disregard what I just said. You'll have a calculator, so you can just plug in 2 divided by 0.5 and get 4 as the answer. Now, our next question is, what is the molarity of a solution made by dissolving 10 grams of NaCl in, again, there's that language, enough water to produce 1 liter of solution? Now, I want to take a moment and look at this right here. Enough water. Okay, yeah, I got that with respect to the volume, but water. Will you guys almost always, or will all of the solutions that you guys talk about be water-based? The answer to that is yes. Basically, everything that we use in our day-to-day lives is water-based. Coffee, water-based. Dr. Pepper, water-based. I don't know if anyone uses any other solutions. I'm being facetious there. I'm just saying the 2 that I use more than anything. So you don't need to worry about in enough benzene or anything crazy like that. If you decide that you want to be a chemist and you go on to take organic chemistry, then you would talk about that sort of thing. And the solutions get more complicated. But for our purposes, what we need to do with this is we need to say, okay, well, we are looking for what is the molarity? That's represented by capital M. Then we need our moles of our solute, which our solute is NaCl. Then we need the volume of our solution, which is 1 liter. So really what we need to do is we need to take this right here and be able to convert it to moles of solute. So 10 grams of NaCl, convert that mass into moles. Now, this information I'm pulling from the periodic table, and it's information that I just remember, but 1 mole of NaCl has a mass of 58.5 grams. So that information, that number, that 58.5, that's coming from the periodic table. So if you're looking at that and thinking, what? That's from the periodic table. I didn't toggle back and forth to show you the periodic table. That's just kind of from recall of doing this sort of problem. And of course, your exams will have your periodic table, so you don't need to worry about that. Now, what we have here is 10 grams NaCl, 58.5 grams NaCl is 1 mole of NaCl. Sorry. So I'm going to do 10 divided by 58.5, pull up my calculator, and what I'm going to get for that is 0.17 moles NaCl. So this amount right here goes right there. So 0.17 divided by 1 is 0.17 molar. Looking at our answer options, is there one that's better than the others? Yeah. 10, 20, 600, none of those are any good. Our best answer option is A. Okay, now when it comes to preparing a solution, so this sort of problem and this sort of problem are good ones for you guys to be prepared to do. When it comes to preparing a solution, which the next few slides, yeah, we've got solution preparation and then dilution preparation. This piece of glassware right here is the type of glassware that you would use to prepare a solution and prepare it accurately. Now, I'm going to zoom in and I think that it's on there. I need a response, a Y or an N. If you look below, actually, can you guys see the hand cursor that I have moving around on the screen? Y or N to the chat. Great. Okay, right now I've got the hand hovered to the right of this piece of glassware. And now I'm going to move it to the left. If you look very closely, can you see that etched line there? Y or N to the chat. Perfect. Okay, so that etched line is super important. And the reason that it's important is because that is what strikes at the heart of this piece of glassware. This piece of glassware is known as a volumetric. Sorry, my volumetric flask. What that means is that, or sorry, let me rephrase that. A volumetric flask is a piece of glassware that's really good for one thing, and that is for precisely measuring a volume. So if you are preparing a solution, you want to be as precise and as accurate as possible. If you look at the bulb of this piece of glassware, it reads out 100 milliliters. What that means is that if you fill the volume of whatever to that line exactly, you have exactly 100 milliliters. Now, it's possible that you're like, oh, well, I've used a graduated cylinder before. Okay. A graduated cylinder is a worthwhile and good piece of glassware, but for as accurate a solution as possible, this is the type of or this is the piece of glassware that you want to use. So in order to prepare a solution, what you would do is you would weigh out the substance. In this case, the substance is copper sulfate, CuSO4. And here, what we've done is we've weighed out 1.2 grams of copper sulfate. So that 1.2 grams of copper sulfate has been weighed out, and you're going to transfer that into a dry volumetric flask. So there's no solution in there, there's no water in there. Okay. After you've added that solid, then you're going to add water. And typically, what people do is they're not very precisely measuring it at this point. Instead, what they're doing is they're saying, okay, I'm going to fill the water to about halfway up the bulb, or get the bulb like half full. Because then what you're going to do is you're going to swirl the solution so that the solid, in this case, the copper sulfate, will go into solution. So it will dissolve in there. So you get the opportunity to kind of agitate it. Much like when you make coffee and you add sugar, you're going to stir it up a little bit. Okay. So this right here shows, okay, well, I can see that the solid has completely dissolved. And now I'm going to kind of repeat this step. But what I'm going to do is I'm going to add water up to that etched line, because that will get me to a point where I have added or I've made a solution that is exactly 100 milliliters. Once you've done that, then you put this cap on there. This is called a penny cap or a penny cap, or a penny stopper, sorry, a penny stopper, because what that's going to do, it's going to prevent, let me write this out. It's going to prevent evaporation. So your 100 milliliter solution will be exactly 100 milliliters. Okay, so if you want, you can kind of think about this as measure your solid, put it in the flask, add water halfway, swirl, 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 add water to etched line, and then penny stopper. Now, you might be looking at this like, I know the first time that I ever used one of these volumetric flasks, I looked at it and I thought to myself, huh, if I add water up to that line, and if I go over, what does that mean? And I'm thinking to myself, kind of as logically as I possibly can, I'm thinking, well, if the water goes above this line, like if I fill the solution up to there, um, answer me Y or N. Do I have 100 milliliters of solution? And this isn't intended to be a trick question or anything like that. If I've added my solution up to this point, no, my solution exceeds 100 milliliters. Okay, so then I gotta go back to the drawing board. Now, or not back to the drawing board, but I've got to like make this solution again. So that's why this is one of the kind of, it's a valuable piece of glassware because it gives you accuracy and precision, but it's also kind of frustrating because if you add too much water and it exceeds this etched line, well, then you haven't made the solution you intended to make. Do chemists have to be that precise? They do, because they want to be as accurate as possible. Okay, so what we would do is we'd take our 1.2 grams of CuSO4, and I will tell you right now, I do not have the molar mass of copper and sulfate down, but I can get them from a web page, so I'm going to do that right now. I'm going to just write them down. Copper is 63.5. So if you're playing along at home, Cu is 63.5. S is 32.1. And then O, well, O is 16, but there are four of them. So 4 times 16 equals 64. So my molar mass for CuSO4 is 63.5 plus 32.1 plus 64. So that gets us to 90. I like to do my math this way. I apologize. 95.6 because that's those two numbers, plus 64 equals 159.6. So 159.6 grams CuSO4 is 1 mole CuSO4. Okay, so then what I'd do is I'd say, all right, well, 1.2 divided by 1.2 divided by 159.6 gives me, I gotta erase some of this stuff and my screen is kind of obscured. There we go, move that there. Pen. That is 0.00752 moles of CuSO4. Okay, 0, that's my number of moles, and divide that by, so 0.00752 moles divided by 0.1. I'll add a 0.1 liters, because 100 milliliters is 0.1 liters. So divide that by 0.1, and I get my concentration of 0.0752 molar. So that would be the concentration of the solution. Okay, now what mass of NaCl is required to prepare 0.5 liters of a 2 molar solution of NaCl? Okay, so this tells us, and I'm just going to set this equation up. So molarity is equal to moles over liters. Well, I like to use this equation and think about what I have. I have my molarity, I have my volume. What I don't have is my number of moles. So I'm going to say 2 molar is equal to X moles over 0.5 liters. So what I'm going to do is multiply each side by 0.5 liters. Multiply this by 0.5 liters. Okay, 0.5 times 2 is 1. So my answer is X moles is equal to 1 mole of NaCl. And if you, I don't know if you remember this from earlier, but we talked about the molar mass of NaCl, and that was, I said 58.5. This was our best answer here, 58.4. It's 0.4, 0.5. It's a rounding difference is what happened there. Now, the last thing that I want to talk about here is dilutions. So typically when we talk about a dilution, we talk about a stock solution. And then we talk about a diluted solution. So I'm going to identify these two. Stock, diluted. What is being displayed here is the progress of going from having, let me scribble this out, scribble this out, scribble this out. Having a stock solution, specifically having 100 milliliters of it, and planning to make a solution. So just imagine that what you have here is you have this stock. Think about this as your super strong Kool-Aid. You made this because you're like, okay, well, I have to make Kool-Aid for, 1,000 people. How am I going to do this? Okay, well, I could either get one packet and 1,000, or no, I could either make 1,000 different solutions. That's one option. Or I could make a super strong solution. And then for every single person who comes up to me, I say, okay, well, get 10 milliliters of this. So, use a graduated cylinder, use whatever, use some piece of glassware where you get 10 milliliters and then you add water to the rest. That will get you the desired diluted version of Kool-Aid. Could everyone give me a Y or an N if they follow that? You make a stock, and then each person will get a small fraction of that. And then they will add water to make that kind of the desired solution. So that's kind of the idea here. Chemists do this with, well, solutions that they make. If you're working in a research lab, you might make a solution that, well, you keep it for 5 years and you just use 5 milliliters of it once a week. Because then what you can do is you can make like a large volume of it and it's stable and you say, okay, cool. I don't need to make that a lot. All I have to do is make it once, add water, make it once, add water. Okay, so what we've got is a super strong Kool-Aid solution. We know the volume of it and we know the concentration of it. What we are going to do is we're going to refer to this as the left-hand side of the equation. Let's say hypothetically that the concentration of this solution was 3.5 molar. Now, that is this right here, 3.5 molar. So if we had 1 full liter, there would be 3.5 moles in that 1 liter. We don't have 1 full liter. We don't really care about how much we have. Instead, when we look at this equation, M1V1 equals M2V2, it tells us the left-hand side is what is the concentration and what volume are you going to take from that? So what we're going to do is we're going to use I'm going to erase this. This is our 3.5 molar solution. My V1 is the volume that I'm going to take from this. So think about this as, you're working somewhere and you've got your big jug of super strong Kool-Aid and you tell each person, hey, if you want Kool-Aid, what you're going to do is you're going to get 10 milliliters of that Kool-Aid. And then you're going to add water to this line on your bottle. So V1 is the volume from that stock that you're going to use to make the dilute version. So this piece of glassware that's coming in here is known as a volumetric pipette. So this is really good at collecting exactly 10 milliliters. So we've gone from our first cell where we've got our stock solution and then an empty flask. Then our next cell right here where we have our stock solution and our volumetric pipette where we get 10 milliliters from that. And now into this third cell where we're transferring 10 milliliters into our previously empty volumetric flask. This is the flask where we are making our dilution. Could everyone give me a number in the chat if you follow, or a letter in the chat if you have a question, or would like me to explain that again? Okay, so we're making this dilution. And from that, or to make that dilution, we're taking 10 milliliters from our first solution. So that is that V1. So we've got what is the concentration of our first solution and how much of our first solution did we use. Now, the right-hand side of our equation, M2 equals V2. Our M2 is going to be, well, what is the concentration of our dilution? And V2 is what is our total volume of our dilution. Okay, so in this case, could anyone tell me, based on this piece of glassware that I've drawn an arrow to, could anyone tell me in the chat what's the volume of our second solution, of our dilution solution? What is the total volume of that going to be based on the piece of glassware that we selected? And it's kind of tough to tell, so I'll zoom in a little bit. That piece of glassware, that's another volumetric flask. And that volumetric flask reads 100 milliliters. So the total volume of our dilution is going to be 100 milliliters. Now, what is the concentration of this? Okay, well, what we're going to do is in this step right here. Oh, in this step right here, what we are doing is we are adding water. So we are adjusting the volume in our dilution solution right here. We're adjusting the volume up to a total volume of 100 milliliters. So we added 10 milliliters of our stock, and then we added water. In this case, it's pretty easy to say, oh, well, we probably added 90 milliliters because we don't have anything that's really dissolving. But it's easier just to say, to use the proper piece of glassware and say, okay, well, I'm going to add water to get a total volume of 100 milliliters. Now, we've got our volume. So basically what we've got is M1 V1 equals M2 V2. Do we know our M1? Do we know the concentration of our initial solution? We do. It's 3.5 molar. What about V1? Do we know that? How much did we take from our first solution? Well, we took 10 milliliters. Okay, so we're good there. Now, next up is M2. Do we know the concentration of our new solution? We don't. At this point in time, we don't. I'm going to put M2. I'm going to put that in parentheses. And then V2. What is the total volume of our dilution? The total volume of our dilution is going to be 100 milliliters. Now, a good question here is, do we have to worry about units? No, we don't. The reason that we don't is because our volume units, milliliters, milliliters, those are going to remain the same. So what that means is that our M2 concentration is going to be in molarity. All that we need to do is say 3.5 times 10. Well, 3.5 times 10 is 35. And then we're going to divide that by 100. 35 divided by 100 gives us our M2 value, which is 0.35 molar. Okay. So that's kind of what there is with this sort of calculation. I am going to do, oh yeah, I'm going to do one more calculation related to this, just to show you another way that you might, that would be good to practice this. And then we're going to talk about percent solutions. Okay, so we've got this now, and this right here is just a calculation that I did on Thursday with that group. I'm going to do basically the same thing. Okay, so another way that we can look at M1 V1 equals M2 V2 is to say, all right, well, I have M1 V1 equals M2 V2. In this situation, I'm going to say I have a 6 molar stock. I have exactly, let's say, 325 milliliters of that stock. And what I want to know is how much dilution can be made with, well, how much, just sorry, I'm thinking of this on the fly. Erase. Yeah, okay, I've got it. How much 0.45 molar solution or dilution can be made. So if you think about M1V1 equals M2V2, effectively our stock concentration is M1. Our stock volume is V1. Our dilution concentration is M2. So what we don't have is V2. V2 equals question mark. And that's what we're trying to solve for. So I'm going to set this up as 6, and I'm going to drop the units because I know what my units are going to be in terms of volume. They're going to be in milliliters. 6 times 325 is equal to 0.45 times V2. So 6 times 325 is 1950. I'm going to divide each side by 0.45. So I'm asking the question, this is almost like saying you've got your super strong Kool-Aid, you have 325 milliliters of it, and your super strong Kool-Aid has a concentration of 6 molar. If you wanted to make a drinkable solution at 0.45 molar, how many or how much could you make? So I'm going to say 1950 divided by 0.45. We're using all of that stock. And what I would be able to make with this is 4,333.3 milliliters or 4.3 liters. So that's another way that you might see this sort of calculation. And I think this is a good way to think about it. Basically, the important part about this sort of equation is, well, when you are doing this, whenever you are doing this sort of calculation, what can you define as your M1 and your V1 and your M2 or your V2? What is the variable that you're trying to solve for? I would also operate under the idea that chances are slim that you're going to have to change your units. Here, I changed it from milliliters to liters. But that's really intentional to show you that conversion, milliliters to liters. Okay, the last thing that we're going to talk about is percent concentrations or percent solutions. If you go to the store and you get isopropanol or rubbing alcohol, chances are it's going to be a percent solution. What that means is that you've got 70% of it is your solute, and that solute is a liquid, and it's dissolved in a total volume of whatever volume. So you would take the volume that is required, the volume of your solute divided by the total volume of that solution. Think about this as like how much of it is water. One way that I always kind of think about this sort of thing is to say, okay, well, I'll think about wine or alcohol or alcoholic drinks. I'll say, okay, a beer, for example, is like 5% alcohol or ABV, alcohol by volume. Alcohol in this case is ethanol. Now, what that means is 5% of this, or let me rephrase that, 5 milliliters out of the total volume being 100 milliliters. So 5 divided by 100 times 100 is going to give us that percentage. Now, if you think about rubbing alcohol, well, most of that 70% solution, sometimes you might get a 95% solution. That's kind of how that shakes out. Now, another thing that you might see at the grocery store from time to time would be a solution like hydrogen peroxide, H2O2. Well, that is going to be a solvent or a solid solute, but then you divide it by the mass of that solution. So typically hydrogen peroxide is a 3% solution. Sometimes you can get like a 20% solution. And then Another thing, sodium hypochlorite, NaOCl, which is commonly known as bleach. That's going to be like an 8.5%. I think it's like 8.25% solution. And all that you do is you take the mass of that substance. So let's say that it's 3 grams of H2O2 divided by, well, the total mass of the solution. And let's say that that's 100 grams of solution. Then you'd see 3 divided by 100 gives you times 100 gives you the percent by mass. Okay, well, that's where I'm going to stop. Um, you might look at these numbers and these calculations and say, oh, could I also calculate this by molarity? Yeah, you absolutely could. I would expect a question that asks about a percent concentration as well as molarity calculate a molarity concentration. Um, but other than that, I'm going to go ahead and stop. I've got office hours starting at 11. I'll hang around for a little bit after I stop the recording if anyone has any specific questions. Other than that, though, I hope you guys have a great Wednesday and I will see you on Thursday. And thanks for coming to class, everyone.